Hey guys, welcome back. Alright, so this is the sixth video in the series. It's the integration techniques. This is pretty much where I left off with my students just before the pandemic hit Montreal, and for historical purposes, March 12th, 2020. So we'll be talking about integration of substitution, the general power rule for integration, and of course the change of variables. Now, these are going to be different techniques that will allow me to anti-differentiate or even evaluate a definite integral using different techniques for more complex functions. So although those basic rules are going to kind of help me out a little bit, there's also different techniques that are required, especially when we're working with more complex functions. So these techniques are going to help us when we work with more complex functions, and not only will they help us with the indefinite integral, they will also help me out with the definite integral. Okay, let's get started with the integration of substitution. Now, the theorem for the antidifferentiation of a composite function. Here, what is extremely important is that you're able to identify a composite function. So just by looking at a function, you should be able to tell if it's a composite or not. So, let's say we have this composite function that's multiplied by the derivative of the function that's been placed inside the other. Then that's the same as finding the antiderivative and evaluating it at g of x, and then of course I'm going to add my constant. So be patient, you'll understand what this formula is used for, and you'll see how we use it. So like we've done in the past, going back to Cal 1, we're letting u equal something. That's where the substitution comes in. Well, if I find du dx, and therefore I end up with the derivative of g of x dx. So I can replace this formula with substituting u instead of g of x. So therefore the antiderivative of f of u du is simply the antiderivative of f, replace u into my antiderivative, and then add c as my constant. So the whole point here is about being able to recognize patterns. So we have to recognize that we have a composite function multiplied by the derivative of the function that is inside the other. So for example, if we take a look at this, we can see that x squared plus 1 all squared is the composite function, and if I were to take the derivative of x squared plus 1, I would end up with 2x. So this follows the pattern that we're looking for. Okay, so let me explain to you exactly what's going on. We have this particular function. Now, earlier we used to call it just simply f of x, but now it has a specific pattern, and it's a composite multiplied by the derivative of what function is placed inside the composite function. And what we're saying is this is the same thing as if we were to find the antiderivative and then plug in g of x into my antiderivative, and then of course add plus c, my constant, to find my antiderivative. So, if we take a look at the previous example, we have x squared plus 1 all squared times 2x dx. This is a composite function. X squared plus 1 all squared is the composition part, is the composite part. And of course the 2x is the derivative of x squared plus 1. So all I need to do to be able to find the antiderivative is simply take the composite part and apply the basic rules that we learned for finding antiderivatives. So therefore I add a power, divide by n plus 1, and I end up with x squared plus 1 cubed all over 3, plus my constant. This is the general form of the antiderivative for this particular function, which is x squared plus 1 all squared times 2x. So what's important is this, that if the pattern follows a composite multiplied by the derivative of g of x, then we simply find the antiderivative of the composite part. So in other words, if it fits the pattern, simply find the antiderivative of the composite function. If I were to take the derivative of what I found previously, I would end up with x squared plus 1 all squared times 2x, which is exactly what we originally began. So the derivative of the antiderivative is simply f of x. There we go. We're done. It's that simple. So the most important thing here is to be able to identify the pattern. Once you identify the pattern and the pattern fits, then you just simply have to find the antiderivative of the composite function. So for these examples, let's take a look. We have x squared, x to the fourth, plus 1 all squared, multiplied by 4x cubed. you're supposed to identify that this is my composite function and x to the fourth plus 1 is my g of x. So if I take the derivative of x to the fourth plus 1, I end up with 4x cubed. So therefore, this fits the pattern, and all I need to do is simply find the antiderivative of x to the fourth plus 1 all squared. The next example, we have the square root of x cubed plus 1 dx. This is a composite function. So therefore, x cubed plus 1 should be g of x. And if I take the derivative of g of x, I end up with 3x squared. Perfect, fits the pattern. All I need to do now is simply find the antiderivative of the square root of x cubed plus 1. And the last example, cos squared x times sine x dx. Now, we know that this is a composite because it's actually cos x all squared. And we know that since that is g of x, if I take the derivative of g of x, I get negative sine x, which is exactly what I have there. So once again, the first integration technique, the first thing that's important is to be able to identify patterns. If the pattern fits, then I just simply have to take the antiderivative of the composite function. Okay, so we're going to use the same example we did in the previous slide, but this time we're going to use the chain rule method to be able to find the antiderivative. Now, we know that this specific pattern is the pattern we're looking for, and this particular example fits that pattern. So technically all I would have to do is find the antiderivative of the composite part, and I would be done. However, using the chain rule. So what we're going to do is we're going to let u equal to x squared plus 1. We're going to take the derivative of both sides and end up with du dx is equal to 2x. Cross multiply, and therefore du is equal to 2x dx. Now, because we're using the chain rule, we're going to now use this formula, which is f of u du. And all we need to do is find the antiderivative with respect to u, and then add that constant. Now, we have u squared du. Okay, where does this come from? Well, first and foremost, du, we know it to be 2x dx. And I also know that u is x squared plus 1, and the composite function is x squared plus 1 all squared. So that's where the u squared comes in. So all I need to do now is simply find the antiderivative with respect to u, which is u cubed over 3 plus c, and then simply replace u with what we did previously, which we let u equal to x squared plus 1. So x squared plus 1 all cubed over 3 plus c. So this is the method for the chain rule, and the chain rule method is extremely important, specifically or especially when you're going to notice that the pattern somewhat is similar, but there's something missing. So we have a similar pattern, but there's a piece of the puzzle that's missing, so I'm going to use the chain rule as a method to find out that missing part. So we're going to do an example where g prime of x is missing something. So for example, we have the antiderivative of x times x squared plus 1 all squared dx. Now, we know the composite part is x squared plus 1 all squared. If I take the derivative of x squared plus 1, I get 2x. But here I only have x. So as you can see, there's something missing. So we need to change the look of the function so that it can be put back in its proper form. How do we do that? Well, we find a way to mathematically change the look of x so that it will actually fit the pattern. And with a little bit of time and a little bit of understanding, you can realize that, oh, hold on a second. If I replace x with 1/2 multiplied by 2x, that is actually equal to x. And now, by doing this, I really didn't change the value of the function. All I did was I changed the look of the function. And now I can simply integrate by factoring out the 1/2 and simply find the antiderivative of the composite part. Okay, let's take a look at some examples. So, we have this first one. It's the integral of x squared minus 9 cubed times 2x dx. Now, there's a product, so that's a good sign. The next thing to recognize is that there's a composite function. Excellent. If I were to take the derivative of x squared minus 9, I would end up with 2x. So this particular function follows the pattern, and all I need to do now is simply find the antiderivative of the composite part. So I would end up with x squared minus 9 to the power of 4 divided by 4, and don't forget to add the constant plus c. Example 2. We have the integral of x times 5x squared plus 4 cubed dx. Now, again, There's a product, there's a composite part, which is 5x squared plus 4 all cubed, and if I were to take the derivative of 5x squared plus 4, I end up with 10x. Well, here's a problem, because I only have x. So therefore, I know that I need to change the look of this function. How do I do this? Well, first I rewrite it in this form. So 5x squared plus 4 cubed x dx. I let u equal to 5x squared plus 4. I take the derivative, which becomes du dx is equal to 10x. And now what I'm looking for is this particular form, which is x dx. So I'm going to solve for x dx. And what I end up with is du over 10. Excellent. Now we use the other formula. So now we have u cubed du over 10. Now du over 10, you have to realize, is like saying 1 over 10 times du. So I can simply factor out the 1 over 10, and now I have u cubed du. Find the antiderivative with respect to u. I end up with u to the 4th over 4, and simply replace u with 5x squared plus 4. Don't forget to add the plus c. Example number 3. Now this one is different. There's really not much we can do here, so it doesn't really follow any of the patterns. So all I do here is simply simplify the function, divide both t and minus 9t squared by root t, and I end up with root t minus 9t to the 3 over 2. And simply find the antiderivative of the first part minus the antiderivative of the second part. In the fourth example, same idea. We have a product, we have a composite, and if I were to take the derivative of t to the 4th plus 5, I end up with 4t cubed. Well, 4t cubed, I only have t cubed, so now I'd have to do that entire process once again. I got to change the look of that function. So what's important to understand is that example 2 and example 4 are what we call change of variables. So in other words, we are changing the variables to u, and we are changing the look of the function so that it fits that specific pattern that I'm looking for. Okay, let's take a look at the general power rule for integration. Now, the general power rule for integration, the theorem actually comes in now, but we've been using this theorem with all the previous examples. So what the general power rule for integration simply says is this. If we have a function that has an exponent multiplied by the derivative of that function, then all I have to do is find the antiderivative by adding a power and dividing it by n plus 1. So we've done all of this, or we've used this general power rule even before we were taught the theorem. A little bit strange to be taught that way, but that's the way it's done. So first we show you how we find the antiderivative, the long process, and then all of a sudden throw you the rule and say, okay, well, here you go, guys. This is the general power rule. However, if we need to use substitution, then we can also use this. So if you have u to the n du, then simply find the antiderivative, u to the n plus 1 over n plus 1, and then don't forget to add your constant. So the general power rule, pretty much we've used it over and over and over again, but through a different process with the last slides and the last examples that we've seen. So taking a look at this one, it doesn't quite look like there's a power, but there actually is a power. The power is 1. So x squared plus x to the power of 1, and the derivative of x squared plus x is simply 2x plus 1. So it actually fits the pattern, and we can simply use the general power rule to figure this out. So all I have to do is recognize that x squared plus x is the u part, and the du is simply 2x plus 1 dx. So, practice in the change of variable. So we have the sine of 4x. How do I know that this fits the pattern? Well, because if I let u equal to 4x, therefore the derivative of 4x would be 4. But technically I have a 1 in front of the sine. So therefore what I'm going to do is I'll let u equal to 4x, take the derivative, du dx is equal to 4, cross multiply, and solve for dx. So I end up with du over 4. Now I can rewrite it in terms of u, and simply sine u du over 4. Du over 4 can be rewritten as 1/4 times sine u, and then simply find the antiderivative of sine u. which is negative cos u. U was 4x, simply replace 4x, and I'm done. Don't forget to add your constant. Okay, the next example. X cubed over the square root of 1 plus x to the fourth. Now it really doesn't look like anything we've seen previously. However, we can rewrite this. So what I can do is I can take the denominator and bring it up and make it a negative exponent. Okay, so it's a product and I have a composite function, or I can take a look at the general power rule. Okay, doesn't matter which one we kind of use to identify. And what I want you to realize is that if I were to take the derivative of 1 plus x to the fourth, I would end up with 4x cubed. But I only have an x cubed. So therefore, once again, there's something missing. Let u equal to 1 plus x to the fourth, take the derivative, and we have 4x cubed. Now, remember what I'm looking for. I'm looking for x cubed dx. So therefore, I will cross multiply and divide, and I end up with x cubed dx is equal to du over 4. Now, I'm going to rewrite the integral both in terms of u. So u to the negative 1/2 du over 4, and then once again du over 4 is like saying 1/4 times du, so I can simply rewrite the integral with the 1/4 factored out. And once again, just simply use the basic rules that we've done before. Okay, I hope that helps. Now, solving a differential equation. In Cal 2, it's set up a little bit differently. They give us the derivative, they tell us what the derivative is equal to. However, when we're looking for a differential equation, we're actually looking for an answer in the form y is equal to something. So what we're going to do here is we're simply going to cross multiply. Excuse me. So dy is equal to 10x squared over the square root of 1 plus x cubed dx. Now what I'm going to do is simply take the integral of both sides. Much like what we did implicit differentiation, where we took the derivative of both sides, well, here we're taking the integral of both sides. Now, just for a side note, you need to remember that the antiderivative of 1 dy is simply y. And that's great, because that's what I'm looking for. I'm looking for an equation in the form y is equal to something. So, rewrite the right side of the equation by bringing up the denominator as a negative exponent. I get 1 plus x cubed to the negative 1/2 times 10x squared dx. And on the left-hand side, I have y is equal to. So far, so good. All I need to do is find the antiderivative of this function. Now, if I were to take the derivative of 1 plus x cubed, I would end up with 3x squared. But I have 10x squared. So to simplify my life, I notice that 10 is a multiple, it's a number, so I can factor out that number. And now what I'm left with is the integral of 1 plus x cubed to the negative 1/2 x squared dx. Okay, once again, if I were to take the derivative of 1 plus x cubed, I would end up with 3x squared. And now I have x squared dx. I'm almost there. I just need to modify a little bit more. So once again, we let u equal to 1 plus x cubed. Take the derivative. I end up with du dx equal to 3x squared. Cross multiply and solve for u. And I end up with du over 3. At this point, we know that du over 3 is the same thing as 1/3 times du. So I can simply take out the 1/3, and I end up with 10 over 3. Find the antiderivative with respect to u to the negative 1/2. So it becomes u to the 1/2 over 1/2. Simplify, replace, and we're done. The differential equation is y is equal to 20 over 3 times the square root of 1 plus x cubed. Okay, so we're going to take a look at the difference between these patterns. So this is pretty much to sum up what we've already spoken about. So the first thing I'm going to do is I'm going to rewrite these two equations. So there we go. We have the integral of 3x squared times 1 plus x cubed to the negative 1/2 and x squared times 1 plus x cubed to the negative 1/2. Now, if we take a look at the first one, we know that we have a composite function, or if you want to take a look at the general power rule to find integration, okay, we can see that 1 plus x cubed, if I were to take the derivative of that, I would end up with 3x squared. So therefore, this particular one fits the pattern, and all I would need to do is simply find the antiderivative of the composite part. For the second example, it's a little bit different. If I take the derivative of 1 plus x cubed, I end up with 3x squared. But I only have x squared. So therefore, instead of working with the first one, I'd be working with the chain rule, or I would find the antiderivative in terms of u. So this is what we call a change of variable. So to sum up everything, if it fits the pattern and there's nothing to be modified, then I simply find the antiderivative of the composite part. However, if I know that there's something missing to be able to find the derivative of g of x, then I have to use what we call the change of variable. Okay, so we're going to take a look at the change in variable for definite integrals. There are two methods for evaluating a definite integral, especially when I have to modify the look of an integral. Okay, so method one, we have our question. We know that we have to change the look of it, so we bring the denominator up as a negative exponent. If I take the derivative of 1 plus 2x squared, I end up with 4x, but I only have x. So now I know that I need to modify the look of this function. So we let u equal to 1 plus 2x squared. We take the derivative. We end up with du dx is equal to 4x. Remember what I'm looking for? I'm looking for x dx. So therefore, cross multiply and solve for x dx, and I end up with du over 4. Okay, now I rewrite the integral in terms of u. I replace the 1 plus 2x squared with u, so I get u to the negative 1/2. The quarter, the 1 over 4, I factored out of the integral, constant multiple rule. And now I find the antiderivative. So I end up with 1/2 times the square root of u evaluated between 0 and 2. Now this is where you need to be careful. If we decide to keep these upper and lower limits, remember that these upper and lower limits were going to be evaluated with respect to x, and now we have with respect to u. So therefore, before I evaluate this definite integral, I have to replace u with 1 plus 2x squared. And now I can simply evaluate this definite integral. I can use the fundamental theorem of calculus and evaluate this, because the upper and lower limits originally were with respect to x, and therefore I have to evaluate with respect to x. So therefore, simply plug in the values, f of b minus f of a, simplify, and you end up with an answer of 1. So, because the question was in terms of x, and my lower and upper limits had to do in terms of x, I needed to evaluate in terms of x. Although I used the change of variable where I modified the question and I let u equal to something, and I found the antiderivative with respect to u, remember that I can only evaluate with respect to x in this case. So therefore I had to first replace u with x and then use the fundamental theorem of calculus. The second method is a little bit different. Okay, the second method requires the changing of both the upper and lower limits. So in other words, I'm going to use the variable u, I will integrate with respect to u, and I will evaluate with respect to u. So it's a little bit different than the first method. We rewrite the equation once again, because I want 1 plus 2x squared to the negative 1/2 times x dx. Once again, I take the derivative of 1 plus 2x squared, I end up with 4x, and now I only have x dx. I need to modify. We use the same process as we used previously. Let u equal this, take the derivative, cross multiply, solve for x dx, and rewrite the equation now in terms of u. Alright, let's continue. We will find the antiderivative and evaluate using the variable u. To do this, we need to change the limits with respect to u. So remember that the lower limit 0 and the upper limit 2 was with respect to x. Now we're going to have to change that. So 0 now becomes a brand new lower limit. We're going to have to change this lower limit because now we're working with variable u. So all we have to do is simply evaluate u. So since x is 0, u is 1 plus 2 times 0 squared, which is 1. So my new lower limit would be 1 with respect to u. My upper limit 2, I need to find a new upper limit. So when x equals 2, I replace 2 into my u equation, and I get 1 plus 2 times 2 squared, which is 9. So now what happens is, because I'm anti-differentiating with respect to u, and because I have upper and lower limits, I'm now changing those upper and lower limits with respect to u instead. So therefore, this becomes my new equation. This becomes my new question. We're going to evaluate u to the negative 1/2 du, but instead of from 0 to 2, from 1 to 9. When I do so, like we did previously, we evaluate and we get the exact same answer, 1. Now this only worked because I decided to anti-differentiate with respect to u, but I also decided to evaluate with respect to u. So let me repeat this again. If we're going to evaluate with respect to x, don't forget to resubstitute x into your equation before you use the fundamental theorem of calculus. But if you decide to evaluate with respect to u, don't forget to change your upper and lower limits. Okay guys, so practice, practice, practice as always. You can go online, you can take a look at some exercises, try to evaluate regarding that specific pattern that we saw, that we looked at, and also try to evaluate using definite integrals and changing your lower and upper limits. So enjoy.